In this video, we are going to see a theorem in invertibility of A in functional analysis. Okay, let X be a normed space and A belongs to BL of X. BL of X is the collection of all continuous linear functions or bounded linear functions. B of finite rank. What is meant by finite rank? If A has finite rank means range space of A is finite dimensional. Okay, then if it is so, then we have to prove that sigma E of A equals sigma A of A equals sigma of A. Sigma E of A is the collection of K belongs to A such that A minus Ki is not injective. Sigma A of A is the collection of K such that A minus Ki is not bounded below. And sigma of A is the collection of K such that A minus K is not invertible. We have to prove that all are same. We already know that sigma E of A is a subset of sigma A of A is a subset of sigma of A. Thus, it is enough to show that sigma of A is a subset of sigma E of A. Why it is enough to show this only? Because sigma E of A is a subset of sigma of A, which is a subset of sigma E of A, right? So, if it is so, then we can write sigma of A equals sigma E of A. And I already know that sigma E of A is a subset of sigma A of A. And here, by this, I will get sigma E of A. This is also a subset of sigma E of A. So, I can say that sigma E of A equals sigma A of A. So, it is enough to prove this thing. To prove this are equal. Now, we are going to prove this with the help of contrapositive approach. We are going to prove sigma E of A the whole complement is a subset of sigma A of A complement. Okay, so let some K belongs to sigma E of A complement, which means what? K does not belongs to sigma E of A, where sigma E of A is the collection of K belongs to A such that A minus K is not injective. So if my K is not in this set, I can say that it is injective, right? So we prove that K belongs to sigma of A complement. That is, we have to prove K does not belongs to sigma of A. K does not belongs to sigma of A means what? I can prove A minus Ki is invertible. Then I can say that K does not belongs to sigma of A. So I am going to prove that A minus Ki is invertible. We are splitting this theorem in two cases. For the case 1, we are considering that my X is finite dimensional, and for the case 2, we will be considering the dimension of X to be infinite. Okay. So, let dimension of X be n. As A minus Ki is injective from X to X by theorem. We know that if F is a linear map from X to Y, F is injective if and only if zero space of F is 0. And if this is the case, I can say that dimension of X equal dimension of zero space of F plus dimension of range space of F. So here, dimension of X equals dimension of Z of A minus Ki plus dimension of R of A minus Ki. So, I know that dimension of X is n. So, n equals dimension of Z of A minus Ki plus dimension of R of A minus Ki. And we know that A minus Ki is injective. Again, by this theorem, I can say that zero space of A minus Ki. Okay, I have written zero space of A minus Ki as kernel. Okay, both are same. Zero space of A minus Ki equals 0. So, dimension of zero space of A minus Ki will be equal to 0. So, this is 0, which means what? Dimension of R of A minus Ki is equals n. We know that R of A minus K is a n-dimensional subspace of X. By this theorem, if W is a subspace of V, then dimension of W is less than or equal to dimension of V, and it is equal if and only if W equals V. So here I can say that R of A minus Ki equals X. So I know that if my range space is equal to my codomain, A minus Ki is on 2. So A minus Ki is on 2, which means what? I already proved that, I already know that A minus Ki is injective. Now I claimed that A minus Ki is on 2. This implies what? A minus Ki inverse exists. So we should prove we have to prove that A minus Ki is invertible. For a linear transformation to be invertible, we first have to prove that inverse exists. Then we should prove that the inverse belongs to the set BL of X. So now we are going to prove that A minus Ki inverse belongs to BL of X. Okay, by theorem, let X and Y be normed spaces. If X is finite dimensional, then every linear map from X to Y is continuous. Here my A minus Ki inverse is a linear map from X to X, right? And my X is finite dimensional. So A minus Ki, the whole inverse, is continuous. If it is continuous and it is linear, we can say that it belongs to BL of X. So I proved that A minus Ki is invertible in case X is finite dimensional. Now we are going to prove that A minus Ki is invertible when X is infinite dimensional. So if I take my X to be infinite dimensional, in this case my K should not be equal to 0. What if my K equals 0? Then I already have A minus Ki is injective, right? Injective means 1 also same. So my A minus Ki is injective. If my K equals 0, then I can very well say that my A is 1. That is, A would be an injective operator. And if x1, x2, x etc. is a infinite linear independent subset of X. Like I can take an infinite linearly independent subset of X, right? Because X is infinite dimensional. So I am taking some infinite linearly independent subset of X. Then A of x1 etc. be a, we were seeing that if my X is infinite dimensional, then I have to prove A minus Ki is invertible, right? We were claiming that x1 x2 is infinite linearly independent subset of X. Then ax1 ax2 are infinite linearly independent subset of R of A. Why this is true? Because if I take some alpha 1 A of x1, alpha 2 A of x2, etc. alpha in A of xn equal to 0, since A is linear, I can write like this. And as A is a linear transformation, it maps the 0 element of domain to the 0 element of codomain. So I can put A of 0 here. And since A is 1, I can write alpha 1 x1 etc. alpha in xn equal to 0. As we know that x1, x2, xn are linearly independent, we can write alpha 1, alpha 2, alpha n to be 0. So this is a linearly independent set. To prove that an infinite set is linearly independent, I can prove it by induction. Like if I prove some n elements in that infinite linearly independent set is linearly independent, I can say that the whole set is linearly independent. So I proved that this is linearly independent if my A is injective. But I know that R of A is finite dimensional. Why? They have already given that A has finite rank, right? So R of A should be finite dimensional. But in this case, I am getting some infinite linearly independent subset of R of A. That is a contradiction. So I cannot have K equals 0. So my K should be non-zero. Let B denote the restriction A minus K to R of A. Like my A minus Ki map is from X to X. Here I am taking my A minus Ki restricted R of A from R of A to R of A. Okay. As A minus Ki is injective, since this is injective, I can say that B is also injective. Okay. Now, as we proved in case 1, if my map is injective, I can say that the zero space is dimension of that zero space is equal to 0, and my dimension of R of B equal to dimension of R of B. This is exactly the same we proved before. So I am writing it just in a simple sentence. So my R of B equals R of A. This is also we have already claimed now. So thus B is surjective as well. Okay. So why this is surjective? Because it equals the codomain. My R of B, range space of B equals the codomain. So B is surjective. Now consider some y belongs to X. Then A of y belongs to where? R of A. This is just a simple thing, right? A of y belongs to R of A. By definition of surjection of B, B is a map from R of A to R of A by definition of surjection. We already proved that B is surjective. Now by the definition of surjection of B, we have some U belongs to R of A such that B of U equals A of Y. So what is B? A minus Ki of restricted to R of A of U equals A of Y, right? I know that A minus K of I restricted R of A equal to A minus Ki for all U belongs to R of A. Why? This is just the definition of the restricted map. So my A of U, I'm just taking this U inside. Why? Because my A is linear. A minus Ki is linear. So A of U minus K of U, Ku equals A of Y, right? So I am taking this A of Y this side. So A of Y, U minus Y equals Ku. Let my x to be U minus Y by K. We find that A of x equals, if I take A of x, I will be getting A of U minus V by K, right? So A of x equals U. And U equals Kx plus Y. Because if I take this K to this side, I can very well say that U equals Kx plus Y. So that is, I can say that if I take this Kx this side, A minus Ki of x equals Y. Which means what? For every Y belongs to X, there exists some X belongs to capital X such that A minus Ki of x equals Y. Which means what? A minus Ki is surjective. Next we prove that A minus Ki is bounded below. Assume that A minus Ki is not bounded below. Okay. Next we claim that A minus Ki is bounded below. Let us assume that A minus Ki is not bounded below. Okay. What if it is not bounded below? Then we can say that K belongs to sigma A of A. This is by the definition of sigma A of A, which is the collection of K belongs to K such that A minus Ki is not bounded below. So my K belongs to sigma A of A. By the result, K belongs to sigma A of A if and only if there is a sequence xn in X such that norm xn equals 1 for each n and norm of A of xn minus kxn converges to 0 as n tends to infinity. So by this result, I have a sequence xn in X such that norm xn equals 1 for each n and norm of A of xn minus kxn converges to 0 as n tends to infinity. Okay. We know that convergent sequences are bounded. So my A of xn is a bounded sequence. In the finite dimensional normed space R of A, right? If R of A, let y1, y2, ym be a basis for R of A. And A of xn equals kn, 1 y1 plus kn, 2 y2 plus etc. kn. And let us assume that A of xn equals kn, 1 y1 etc. kn, ym. This is because it is an element of R of A, so I can write it with a linear combination of y1, y2, ym. Then by theorem, let y1, y2, ym be a basis for y and xn is a sequence in y if my xn equals kn1, y1 etc. kn, ym. Then xn converges to x equals k1, y1 etc. km, ym if and only if k and j converges to kj. Like it should converge coordinate wise. Also xn is bounded if and only if kn, j is bounded. So also I know that by Boltzmann-Weierstrass theorem, every bounded sequence in k power n has a convergent subsequence. With the help of these two theorems, I can say that k, n, p, j converges in k as p tends to infinity. So again by theorem star, again with the help of this theorem, if my k, n, p, j converges, I can say that A of x and j converges. Okay. From Boltzmann-Weierstrass theorem, I have this bounded sequence k and j. First of all, I had some thing like xn, a of xn equal to some linear combination, right? From there I already know that a of xn is bounded, so I can say that k and j is bounded, and then by Boltzmann-Weierstrass theorem I can say that as it is a bounded sequence in k power n, I can say that it has a convergent subsequence. That convergent subsequence I am taking it to be k and p comma j. That is a convergent subsequence in k. Then again by using this theorem, if my k and j converges to kj, then I can say that xn converges to x. Again by using this theorem, I can say that a of x and j converges. I am saying that a of x and j, like this is a subsequence of kn and this is a subsequence of a of xn. Okay, this is a subsequence of a of xn which converges. So I'm taking that to converges to some y. So if this converges to y, then my k, x and j also converges to y, right? So norm of, if I take norm of y, then y equals limit j tends to infinity k, x and j, right? From this. So if I use the property of norm, I can take my scalar k as mod k, limit j tends to infinity norm of x and j. But I know that all my x and norm equal to 1 for all n. So this is, if this is 1, then I can say that it is equal to mod k. But I already proved in the first few moments that k not equal to 0. So my mod k not equal to 0. So I am here saying that norm of y not equal to 0, which means that y not equal to 0. But if I consider my a of y, a of limit j tends to infinity k, x and j, which is equal to k into limit j tends to infinity a, x and j. But I know that a, x and j converges to y. So this is ky. So a of y equals ky means a minus ki of y equals 0. Since a minus ki is injective, as we already know that a minus ki of y equals a of 0 implies y equal to 0. But this is a contradiction, right? So I can say that a minus ki is bounded below. But by the theorem, if my x is a normed space and a belongs to Bl of x, a is invertible if and only if a is bounded below and surjective. So here my a, I already claimed that a minus ki is bounded below and it is surjective. So I can say that a minus ki is invertible.